Just talking about today is about bentonite polymer composite GCLs for aggressive conditions, dealing with leachates that are different from municipal solid waste leachate, that are characteristic of what we might see in coal combustion products, mine facilities, radioactive waste facilities, bauxite liquor from red mud facilities, different types of very aggressive liquids. Can you see the slide there? Is it turning? Just want to check in. Can you confirm?
Yes.
Okay, good. Sounds like we're in good shape. So I mentioned we have 4 different webinars. This is the second of 4. I think we talked about those today. And we will have the CEU credits that will be coming out. So look for the email from me with other materials as we mentioned. And let's move on to the next one. All right, so let's talk about our topics today. So we're going to talk again about conventional GCLs that we did last time with sodium bentonite that have low hydraulic. When do they have low hydraulic conductivity? When do they not? And when they are more permeable, what do we do? What type of products can we use? And why do bentonite polymer composite GCLs fit into that category of a GCL that can work with much more with aggressive liquids, which are much too aggressive for a conventional GCL? Why do they work? And how do they work? We're going to talk about a issue called polymer elution, which is essentially where some of the polymer is released from the bentonite polymer composite GCL, how that affects hydraulic conductivity and service life. And then finally, how can I determine if the BPC-GCL that I'm looking at will have low hydraulic conductivity to my leachate? We'll talk about some basic ideas about chemical compatibility testing. All right, so let's step into the meat of this. We looked at this slide last time, and I like to come back to it because if we think about geosynthetics, the role of geosynthetics in environmental containment systems, they really revolutionized our ability to contain waste. First, the use of geomembranes with compacted clay liners to create composites, where we have for example, a 60 mil geomembrane or 1.5 millimeter geomembrane over a compacted clay layer that's 600 millimeters thick and has a hydraulic conductivity of 10 to the minus 7 centimeters per second. That composite liner really changed the state of waste containment systems and their ability to protect the environment. Over years, that system has evolved through technological developments with greater and greater use of geosynthetics. And one of the really significant innovations has been the GCL, the geosynthetic clay liner. We replaced this clay liner, which is on the order of a half to a full meter thick, depending on what part of the world we live in, and we replace it with a very thin GCL that we see here on the right. Now, I want to ask, can you see my cursor? Since I'm not using presenter mode, I don't have my laser pointer anymore. Can someone confirm that? You can see my cursor?
Yes, we can. Thank you.
Thank you. Appreciate it. So we replace a very thick compacted clay liner with a thin GCL, which is pretty remarkable if you think about it. Not only is it thinner, which saves us airspace, but it tends to, in many areas, it can be less expensive to construct. It can be more readily constructed, and we can construct it with fewer flaws. So we can really create a system which is much more environmentally protective and less costly using a GCL in lieu of a compacted clay liner. If you think about that, it's pretty remarkable. We replaced this thick clay liner, as I've shown here, with a thin GCL. And over here on the right, a GCL product, a couple of photographs. We essentially bring this in rolls, install it almost like a carpet. We're rolling it out, we're overlapping it, we're filling the overlaps with bentonite, and then we place the geomembrane on top of it. And when the GCL is swollen, it's on the order of 6 to 8 millimeters thick, and that very thin system has equal hydraulic protection as this much thicker system for a compacted clay. Now, for that to happen, because we still will have the same amount of liquid on top of it, that GCL has to have much lower hydraulic conductivity than a clay layer, about 100 times lower. And typically in the 10 to the minus 9 centimeters per second, if you're working in the United States, or 10 to the minus 11 meters per second in the rest of the world. Well, what makes that happen? And we talked about this last time. So those you're on last time, hopefully you remember this. If you're new, this will hopefully be something you'll catch very quickly. But what makes a GCL have such low hydraulic conductivity to essentially be impervious? Because we create a GCL, we've got two geotextiles, we put granular bentonite or powdered bentonite between those two geotextiles, and then we needle punch it, we join it. And of course, the geotextiles are carriers, right? They're there to essentially provide a mechanism to get the bentonite layer in place. They also provide shearing resistance for interfaces against the other materials in the barrier system, both on the surfaces and internally with the needle punching fibers. But what's truly remarkable is we take a particulate material, and this is true whether it's a granular bentonite or a powdered bentonite, which would be fairly permeable. This looks like sand-sized particles, something that would be very permeable in the context of just looking at the porosity of the bentonite granules that we see in the GCL. For this to be effective as a hydraulic barrier, those bentonite particles have to transform. They undergo swelling, and in fact, that's what I show here on in the lower right. It's actually a GCL that I exhumed from one of my field sites in the Sonoran Desert of California. Even in one of the driest, hottest deserts in the United States, there's enough moisture in our systems to hydrate that bentonite and cause the bentonite to swell and form a gel. We go from a very pervious material shown here at the top with large pores to essentially an impervious material down here at the bottom with a gel where all of those pores are close to what we might call nanoscale pores. And I always say that geotechnical engineers were the first experts in nanotechnology in the world. So why does this happen? And when does it happen? And in fact, if it doesn't happen, this transformation from a particulate material to a gel, it will be much more permeable. Why does that happen with bentonite? This isn't any clay that this would happen with. It's got to be something special. Well, what's going on? Well, if we looked at those particles within the GCL more specifically, we would see a contrast depending on the geochemical conditions. I show here on the left a condition where those particles swell. Each particle, you can imagine, moisture is going to get associated with it. It's going to begin to swell, and eventually the pores between them will close, and they'll essentially look like one material. And the pore pathways through which water flows will be extremely small and tortuous, as I've shown here. And that gives us very low hydraulic conductivity. And so that particle has to swell, and in fact, it swells many times its original volume. On the other hand, if the liquid that contacts the GCL has a chemistry that prevents that from swelling, and those particles only swell modestly or not at all, and we'll see some examples of that in a minute, then the large pores will remain, and the hydraulic conductivity, the pathways will be large and less tortuous, and the hydraulic conductivity will be much higher. So contrasting conditions, we have to have that swelling phenomena to work. And this occurs with bentonite because bentonite is predominantly comprised of the mineral montmorillonite, which I show here on this slide. What's special about montmorillonite? Montmorillonite makes up about 70–80% of most bentonites. Montmorillonite's a really truly special clay mineral. It's created from a series of stacked 2-to-1 mineral layers consisting of a silica tetrahedral sheet and a gibbsite octahedral sheet that create a so-called 2-to-1 element. That's what I show here in this upper part of the diagram on the left. And that sits in a stack. There'll be a whole series of those. And what's special about montmorillonite is when that system hydrates, this so-called inner layer region allows water molecules to enter. Water molecules enter that region and the sheets separate, they swell. And in fact, they swell a dramatic amount, maybe 10 times their original volume. And so when this system hydrates and swells, in fact, we may have more water. In fact, we do have more water in the GCL than we have solid. The volume of water may be larger than the volume of solid, primarily because those sheets can separate as water molecules make their way in. That's the swelling phenomenon. That's the magic of bentonite that makes it effective. And that's true whether it's a powder bentonite like I show here on the right, or a granular bentonite as we see in some of the earlier diagrams. When does that happen? Well, the swelling that we rely on is something that's called osmotic swell. And there were really fundamental studies on this done many, many years ago in the 1950s on the behavior of montmorillonites and their swelling in different aqueous solutions. There was a professor named Norrish in 1954 published a classic paper, which I've extracted this graph from, and I replotted his graph. I didn't think they had these nice color graphs back in the 1950s. But he looked at that with so-called D001 spacing, which is essentially directly related to that inner layer of spacing between the sheets that I showed in the previous slide. And that's essentially corresponds to swelling. As D001 gets larger, we have more and more swell. And he plotted that versus this really strange, only academics can make graphs like this, creating unusual axes to get linear lines or linear data sets. And he plotted it versus 1 over the square root of his salt concentration that he did his experiments with, all right? And so on the left, at 0 on the x-axis, that's a really concentrated solution, infinitely concentrated. And over on the right at 10, and even farther to the right, it's essentially infinitely dilute. So we're going from concentrated on the left to dilute on the right, and on the y-axis from very little swell to very high swell as we go from bottom to top. Well, what happens when a bentonite hydrates? And this is where it's really very critical to think about the compatibility of the leachates that we have to contain in the materials that we're used to contain them in a GCL. The hydration process goes through 2 steps. The first part's called crystalline swelling, when moisture first begins to affiliate with the clay surface. And that just causes a very modest amount of swelling in that inner layer, very, very modest. And that occurs regardless of conditions. And then there's a second phase called osmotic swelling, and I've got that separated here by a dashed line, whereas more and more water molecules are added to that inner layer and it just expands. And it's this osmotic swell that creates the gel that makes bentonite special. It's the magic in bentonite. Now that osmotic swelling only occurs when the chemistry of that inner layer area, the liquid and the surfaces associated with that liquid, are predominantly associated with monovalent cations, or cations are positively charged ions that have a charge of +1. That's sodium, right? We use sodium bentonite out of a mine in Wyoming. It swells dramatically because it's a sodium bentonite when we put it in water. In fact, the more dilute the water is that we add to the bentonite, the more swelling that will occur. So we'll get a lot of swell in a dilute solution, but as the concentration goes up or it becomes more concentrated, we get less and less swell. And in fact, if it's too concentrated, we'll get very little swell at all. We may only be crystalline. Moreover, if we have divalent or polyvalent cations, or ions in solution that have a charge of +2 or higher, if they're predominant, we will only end up getting very little or crystalline swelling instead of the osmotic. So you can imagine that the propensity for that GCL to form a gel is going to be really sensitive to the chemistry of the solution that we're dealing with. Now, the classic things you might see in your first course in soil mechanics, when we put the dry bentonite in a graduated cylinder of water, we do that with deionized water, essentially infinitely dilute. It swells enormously. But we don't contain deionized water in containment facilities. We contain contaminated liquids. Municipal solid waste leachates tend to be not too concentrated. and they tend to be predominantly monovalent. And for that reason, conventional GCLs work really well. They swell a lot. In contrast, for example, if we're dealing with a very a coal combustion product, for example, a coal ash landfill, we may have a very concentrated solution that may be predominantly divalent cations, and it won't have any swelling at all. So we may have very different conditions. We see this behavior that I showed in this previous slide graphically, vividly in the photographs here that I took a number of years ago, but I just love these photographs, so I continue to use them. These were swell index tests that we did with the old GRI GCL1 swell test, where I essentially put a patty of bentonite inside a Proctor mold and then pour water on top of it. And we then we have a little pad on top of the bentonite and a dial gauge, or LVTD these days, and we measure the swell. And depending on the water that we add to that test, we might get a patty like that I show on the top here, a very thick, swollen GCL. And it looks like in this particular application, I'm going to make this a touch bigger. Hopefully you can still see it. But we can see that the bentonite here has swollen to about 40 millimeters, where the original thickness is about 6. All right. We don't see any remnant granules. We just see a gel. That's a very impervious bentonite, and that's in deionized water, right? So there's no ions in that water to affect that sodium versus calcium balance, or monovalent versus polyvalent that we talked about. And it's really dilute, so it swells dramatically. On the other hand, if I do the same exact experiment, I put a thin layer of bentonite in the bottom of my Proctor mold. I put a plate on top with a dial gauge or an LVDT, and I pour a 50 millimolar calcium chloride solution, and calcium is a divalent cation. If I put that solution, a more concentrated solution that has divalent cations as opposed to no cations or monovalents, I get no swelling. In fact, look at that patty from this 50 millimolar calcium chloride experiment. It's about 6 millimeters thick. It doesn't look like it's swelled at all. Well, it's only gone through the crystalline swelling component because it's calcium and it's more concentrated. So essentially no swell with the concentrated divalent solution, enormous osmotic swell with the DI water. And that makes all the difference. That makes all the difference in the behavior of GCLs. So let's take a look at what we do today for swell index tests. We shared this last time, and again, I'm not able to use presenter mode, so I'm just changing the size just a touch there. Apologize for that. But we normally measure this with a swell index test, and we'll talk about these a little bit later on, but I just wanted to bring it back. We use 2 grams of dry bentonite that's been ground to pass, I believe a number 60 sieve, and we sprinkle that into the solution of interest in the graduated cylinder, and then it swells, and we measure the swelling of that bentonite. And in this particular case, it looks like it's about 18 milliliters in that graduated cylinder. That's the lower red bar. Depending on the quality of the bentonite and the solution, we might get up on the order of 34 milliliters or 32 milliliters, as I show here. But what's remarkable is that this small volume of dry bentonite that I show here on the left swells such a dramatic amount, Now, if I put a concentrated solution in here, it'll swell, go through crystalline swelling, and it'll go to 6, maybe 8 milliliters per 2 gram and no more. Well, why is this relevant? Well, we know with conventional GCLs, they work really, they're fantastic products. And for example, in municipal solid waste facilities. Municipal solid waste facilities have moderate concentration. They have a potpourri of ions in them, organic contaminants, inorganic contaminants, but they tend to be monovalent. We have sodium, which is predominant, and we have ammonia that's a predominant. Those are both monovalent cations. And that middle of this graph here is the MSW. We're going to talk about what this graph in a minute. This sweet spot right in the middle is fantastic for conventional GCLs. Now we can see here on the axes two different variables I talked about last time. The one on the x-axis is so-called ionic strength, or I. Ionic strength is essentially the total concentration. We add up all the different concentration of all the different ions in solution, and we balance them by their the charge. And so, for example, a divalent has greater influence than a monovalent because it has additional charge. And I show the equation for ionic strength up here on the right. But essentially, think of ionic strength as just aggregate concentration on the x-axis. And on the y-axis, I have something called RMD, or the ratio of monovalent to polyvalent cations. And that equation is shown here on the right as well. Monovalent on the top and polyvalent on the bottom. And it has a weird square root in there, and there's historic reasons for that. And you can see it has a D in there originally as well, because in our original work, we started off with divalent cations only, but expanded it to polyvalent cations later on. On this graph, as we go from bottom to top, the low RMD is very divalent. The high RMD is very monovalent. And as I mentioned, the MSW leachates that are in the middle are right in that sweet spot. It's not too concentrated and it's not too divalent. And for that reason, we get really good osmotic swelling and we get very low hydraulic conductivity. But once we get out of that space, we can get really different conditions. So for example, we might have coal combustion product leachates, which are much more concentrated. And in fact, I made this graph a few years back. We now in our laboratory get coal combustion products leachates that are off the chart. They are way up here. They're just so strong, some of those leachates. They're like a syrup. Bauxite liquor from aluminum refining facilities. Aluminum, when we refine bauxite ore, we blend it with pH 14 sodium hydroxide to essentially dissolve the ore. That creates a very strong leachate that we have to manage. Again, bauxite liquor is another one. Some hazardous wastes, some pot liquor leachates up here that I show on the right. All of these are much more concentrated and will suppress that osmotic swelling and prevent the low hydraulic conductivity from occurring. Another example doesn't have to be concentration. It normally is. Normally, aggressive leachates are driven by high ionic strength. But there are applications where it's just changing the valence. And this is an example here, as I show down below. Same total concentration as MSW, but the low-level waste leachates tend to be divalent. They tend to be divalent. And as a result, that divalency will suppress osmotic swelling, and they can be much more permeable than we would get for similar concentrations with an MSW leachate. So even these less concentrated solutions, just changing the valence will render our conventional GCL ineffective, and we have to use something else. And just an example of this, the influence of ionic strength with coal combustion product leachates. I like to show this just a couple of different conventional GCLs we've tested. We've got hydraulic conductivity on the y-axis, ionic strength or aggregate concentration on the x-axis. And we see here as we go from deionized water, low ionic strength, up to really concentrated trona ash leachates on the right, the hydraulic conductivity increases orders of magnitude. And in fact, even at similar ionic strength in the intermediate range, as I go from a typical coal ash to a more divalent coal ash, the conductivity jumps in order of magnitude. It's predominantly ionic strength, but cation valence can be influential as well. But for most cases, it's ionic strength. So what do? I have a liquid that I have to contain. Essentially, my bentonite won't swell in, and the bentonite has to swell for the GCL to be effective. Well, that's where polymers come in. And there's a lot of different types of polymer bentonites. We're going to talk about those in a minute, but we're talking here about Bentonite Polymer Composite GCLs. These are the predominant products you see on the market in North America today, but also we see them in Australia, we see them in parts of Europe, parts of Africa as well, and also very significantly in China these days. And a bentonite polymer composite is where we take bentonite, which I show here in this upper photograph, and a particulate polymer. We blend them together and we create a composite material. They're a composite material because there's two pieces that are working together, a polymeric component and a bentonite component that are working together, but they're also working as two separate phases. And we'll talk about that in a minute. And these materials will work in the concentrated leachates that a conventional GCL will not. And I got to give some credit to Joe Scalia, who made an original version of this slide and clipped these photos. Joe Scalia is a professor at Colorado State University, and Joe did a lot of the seminal work on bentonite polymer composite GCLs for his PhD years ago. And thank you to Joe for creating an early version of that slide. So how do these materials differ from all the different bentonite polymer mixtures that we see out there? A bentonite polymer composite material is so-called phase separated. We have granules of bentonite and we have particulate polymer. We blend them together as two dry materials in a GCL and we deploy it. And as moisture moves into that GCL, both the granule hydrates and the polymer hydrates, but they hydrate independently and they form two separate phases. And it's that gel from the polymer that sits between the bentonite granules that does all the amazing work in bentonite polymer GCLs. That's a very different material than what I show here in the middle, which is a polymer modified bentonite, or so-called intercalated bentonite, where we've got some expansion of the mineral. So I've got individual sheets here, and you can see they're a little expanded as opposed to in my granules over here, which are compressed. And I've actually got some polymer molecules inserted in between the bentonite sheets. That's a so-called intercalated polymer modified bentonite. That's a different type of material. We see this in some of the European products, and we see this in some of the Asian products as well. And on the right, we see another type of polymer modified bentonite, a so-called exfoliated product, where we actually really put a lot of energy and separate out the mineral sheets and wind polymer molecules all around those sheets. That's another type of polymer bentonite. These on the right are different. They have lower polymer loadings and they function differently. Essentially, in the polymer modified bentonites that I show here, we're modifying the surface of the bentonite to give it different properties. In contrast, in bentonite polymer composite, we actually have a true composite material. Two different phases working together collaboratively to achieve low hydraulic conductivity. So the bentonite polymer composite is so-called phase separated. Where does this begin? Well, it begins with a dry mixture of two different materials. The granular bentonite, or could be powdered, but most of the products that we've been working with are granular. And I show, this is a typical granular bentonite from a GCL shown here on the left, and a typical polymer particulate shown here on the right. And these two different materials are blended together, typically about 4 to 8% mass of polymer, and the rest of it being dry granular bentonite. Those two are blended together and as a mixture put in between the geotextiles and the GCL. And as it hydrates, these particles change form, as we talked about as well. The bentonite particles swell, the polymer particles hydrate, and they affiliate with water molecules. We'll see some photographs of that in a minute. And it's those processes that give bentonite polymer composite materials their efficacy in GCLs. Now, the type of behavior we get depends on the type of polymer, and this is kind of the secret sauce in a lot of bentonite polymer composite GCLs, and these are all proprietary. Manufacturers won't tell you what polymer they're putting in their products because that's a trade secret, and that's understandable. But there are different types of polymers that could fit into broader classes of materials. We either have so-called cross-link polymers or linear polymers, the two most common types of polymers that we'll see in bentonite polymer composite GCLs. They behave somewhat differently. When water molecules affiliate with these different polymers, we get a different characteristic type of hydrated polymer in the pore space. Shown here on the right with a so-called linear polymer, we see that we get a kind of what looks almost like a very viscous fluid or a gel, almost like a greasy type material shown here with this hydrated linear polymer being pulled out of a jar. Whereas on the left, we show with the cross-link polymer, it doesn't form quite as much of that kind of almost gel or fluid type structure. We just see each of the granules tends to swell on its own. So it doesn't form quite as much of a uniform type of material. It looks more like hydrated particulate. And that has some different impacts on the behavior of these materials. We'll also see so-called superabsorbent polymers as well. And superabsorbent polymers may be cross-link or linear, but they're polymers that not only do they hydrate, but they have a high affinity for water molecules. They tend to want to bind lots and lots of water molecules, and they swell a lot. In contrast, many of the other so-called cross-link or linear polymers used in BPC-GCLs swell very little. Many of you who are parents are familiar with superabsorbent polymers. They're commonly used in baby diapers. And that's a great example of a high ionic strength concentrated solution that we want to contain very carefully and very effectively. As we look at these materials in GCLs, we see they look somewhat different when they're using a GCL. GCL with a BPC-GCL with a cross-link polymer, we'll actually see bits of particulate gel within the GCL when it's been hydrated. You can just barely see it here. I wish I was in presenter mode to blow it up a little more. But we have those crystals of particulate hydrate and affiliate with water, bind water, but they tend to be very distinct. In contrast, with a linear polymer, we won't see that type of clarity of the bentonite versus the polymer in the cross section, but it's very much there as a separate phase. Regardless of the type of polymer that we're using, what's important is this so-called polymer gel that forms. That particulate material, water molecules are hydrating the surface of the polymer and it forms a gel. And that you can imagine, just as we looked at earlier, how we had the pore space in the bentonite that had open pores between the bentonite granules, and we're filling those pores with this viscous, goopy material that doesn't flow very well. All right, and that's the so-called polymer gel. All right, and that polymer gel does all the work in blocking the pores and controlling the low hydraulic conductivity. So if a bentonite granule swells a lot, we don't need much polymer to fill those pores. But if it swells modestly, we need more polymer. So the two different components work together. So a macroscopic photograph here shown on this slide. We'll look at a scanning electron micrograph next. And thanks to Q.O. Tian, assistant professor at George Mason University, who took this photograph a number of years back when he was working for me with his PhD. But where we have clusters of bentonite from our granules that are swelling only modestly in this particular liquid, and then we see the polymer binding between them. Now the polymer looks like strands here because this is a scanning electron micrograph where you actually have to dehydrate the system before we can take the photograph. And so the water molecules have been pulled out of that polymer structure using a so-called environmental SEM, which retains the structure, but allows us to see the polymer, but doesn't have the issues that a conventional SEM would have with water. But you can see the polymer here. It's filling the pores between the bentonite. It's doing that job of essentially clogging the system. And that's effectively what the polymers are doing. That 5% of polymer that we're adding essentially clogs up the pores within the bentonite. So let's think about this. Let's think about this a little bit more. This is really important because this is the fundamental basis on which these materials work. So on the left here, I show conventional GCLs with conventional sodium bentonite. And if I'm in a leachate, like municipal solid waste leachate, I get lots of swelling of the bentonite granules, as we saw earlier, tortuous pathway, very low conductivity. On the other hand, if we're in a leachate that's more concentrated or very divalent, for example, a coal combustion product leachate, the bentonite particles don't swell, the voids remain open, and the pathway is much more, less tortuous, more open, and it's higher hydraulic conductivity. our BPC-GCL functions by filling these pathways here. And we see that over here on the right in diagram C. That we fill that pore space between the granules with a polymer gel that swells with the leachate. So the two are working together. Now the bentonite granules aren't going to be essentially inert. They are going to swell, but they just don't swell as much as they do in a dilute solution. And so the polymer is kind of making up the difference and filling in the pore spaces that don't swell shut. And it's critically important. That polymer creates this very tortuous flow path with very low cross-sectional area that drives the conductivity down to very low levels. It's a pore clogging phenomenon. What's important is that polymer has to stay in the pores. If it is drawn out or pushed out by the hydraulic gradient, it will become more permeable. And we call that so-called polymer elution. So if that polymer would flow out, and it is a gel, it's not a solid, it can vacate the pore space and the GCL can be more permeable. So the polymer that we're going to choose is going to have to match up with our leachate so that it has properties that prevent that polymer from wanting to flow out under the conditions that we're going to be imposing on the GCL with a particular geochemistry. Now, how do these work? Let's look at some data. This is some data example for coal combustion product leachates for work that we did for the Electric Power Research Institute, and Nick Chen, who's a postdoc of mine, soon to become assistant professor at University of Central Florida, did this work for his PhD years back. But he shows a couple things in this graph, and I can't use the animation because I'm not in presenter mode, but I'm just going to have to talk through them. So I've got two different types of data in this diagram. All right, I've got sodium bentonite, which is the gray circles, NAB, conventional GCL, all right? And then I've got a series of different bentonite polymer materials, and these are commercial products shown here with CP or GP, depending on the material we were looking at. And I also have a number behind that that corresponds to the polymer loading. So the CP product only has 1.2% polymer by dry mass, a very small polymer loading, whereas the one at the bottom here at GP has almost 11% polymer, a lot of polymer in it, right? So very different materials with different polymer loadings. And this one at the bottom is one of the early BPCs. It has around 14% polymer loading, really, really high. So a couple important points here, and I wish I had the animation, it would show up a little bit better. But you see that the data fall into two different groups. The group here with that I've got shaded with this gray kind of almost like an ellipse around it. And then the other group of green and blue and red points, which have a band shaded light blue. Now the band shaded in gray has the sodium bentonite in it. It looks like we saw before. As the ionic strength goes up, the hydraulic conductivity goes up right along with it. We see the same phenomenon for bentonite polymer composite GCLs if they have very low polymer loading. And that's what I show here, the CP 1.2. This is an early BPC product with very low polymer loading. You can see these blue triangles. It's a bentonite polymer composite, but really the hydraulic conductivity is no different than the rest of these sodium bentonite data points show with gray circles. The blue triangles and gray circles are essentially indistinguishable. Why is that? Well, neither of them has bentonite that's swelling sufficiently, and CP 1.2 doesn't have enough polymer in the pore space, right? So there's not enough polymer there to fill the void, so the water can flow through, or the leachate can flow through very readily. If I increase the polymer loading more, I get a very different behavior. And in fact, that's what I see here in the material that's shaded in blue. In fact, I get hydraulic conductivities for these CCP leachates that are essentially independent of the concentration of or the ionic strength of the leachate. Very low hydraulic conductivities from dilute solutions to very concentrated solutions. Regardless, as I go from dilute to concentrated, I remain very low hydraulic conductivity in that blue band. But there's a breaking point. Even these materials don't work everywhere. And in this particular case, when we get out to about 1 molar, that's a pretty strong solution, they become much more permeable. So in contrast to a conventional GCL, the hydraulic conductivity is increasing gradually with ionic strength. As I show here, the gray band, these materials are more a very almost like a brittle type of material. You can imagine impermeable to a point, we get it too concentrated and they become just as permeable as the conventional GCLs, or almost as permeable. So I show that with cold combustion product leachates, and here's just another with actually a new paper we have out in geotextiles and geomembranes, just coming out right now. It's online, it hasn't been in the press version. Shows similar type of behavior for bentonite polymer composite GCLs permeated with bauxite liquors. And these are bauxite liquors from the United States, China, and other parts of the world. And we see in this particular case that the sodium bentonites shown here in gray, much more permeable than the BPC-GCLs. The other thing that we see is for the very concentrated bauxite liquors, some BPC-GCLs are very impermeable, here around 10 to the minus 12 meters per second, or 10 to the minus 10 centimeters per second. That's really impervious, to being much more permeable around in the 10 to the minus 7 range. So it can vary depending on the polymer loading and the type of polymer that we use. Let's talk about polymer loading for a second. As I indicated earlier, there's a threshold. We have to have enough polymer in the pore space to fill the voids and drive the hydraulic conductivity down. And we show that here in this graph. There's some early work that we did with low-level waste, low-level rad waste leachates, and just showing how the hydraulic conductivity of the GCLs vary with polymer loading. And here, it was right around 4 or 5%. We got the 5%. The GCL tended to have very low hydraulic conductivity, whereas if it had less than 4%, the hydraulic conductivity was much higher and comparable to that for a sodium bentonite. So polymer loading is very, very important. We need to validate that during manufacturing and probably during construction quality control as well. And we've actually just published some new information on how to measure polymer loading that'll be coming out in Geotechnical Testing Journal within the next month or so. Not quite online yet, but so polymer loading is really important. We have to have enough polymer to fill the pores, to clog the pores. Not only do we have to have enough polymer, but the polymer needs to stay in place. If that polymer tends to flow out of the system, or so-called elute, we call it polymer elution, the hydraulic conductivity can increase dramatically. And that's what we show here in this particular slide. We have hydraulic conductivity on the y-axis on the left graph, and on the x-axis, cumulative polymer elution per mass of bentonite. As we see, as more of the polymer is lost, the system becomes more and more permeable, increasingly permeable. And we see here on the right another example, just with different solutions, hydraulic conductivity on the y-axis, percentage of the polymer eluted. With very little elution, we retain low conductivity, but if we have substantial elution, it becomes much more permeable. So our ability to retain the polymer is going to be critically important. What happens when the polymer elutes? Well, given our diagrams from we saw before, you can imagine we get a flow path through the GCL that opens up, right? Because the bentonite granules aren't swollen, and if the polymer that's filling them in elutes, they will become much more permeable, and that's what we see here. This is an example of a GCL where the polymer we were using was not compatible with the leachate that we were trying to contain. And we can see that early on this experiment, the GCL was really impervious, but over time, this is actually several different products that we did tests with, as the polymer flux, or the amount of polymer being eluted from the system, increased, the system became much, much more permeable, right? And the reason for that is we have flow paths open up like we see here on the right. And one of the things that we always do when we get a bentonite polymer composite GCL that's too permeable, at the end of the test, we run Rhodeman WT dye, we spike the influent, we run the dye through it to be able to determine where the flow is going and understand the behavior of the GCL. We also do that to check that we don't get sidewall leak, which can inevitably happen in laboratory testing. But here's an example. You can see in this upper photograph a preferential flow path, just a tiny little dot in the GCL where the liquid is flowing through. And it's down here, and that's another example. You can see a preferential flow path right here as well, right through the GCL. The polymer has eluted out of that pore space and it's become much more permeable. Here's another example where we're looking at the GCL from the surface. And we can see in this particular example, in this essentially pie piece of the GCL, all the flow has been going through these localized spots. And it turns out it's in this pie piece that has the lowest polymer loading in this particular example, 3%. In this example, as indicated before, somewhere around 4 or 5% probably is the minimum threshold that we want to see. And so if it does elute, we will get a system that will be more permeable. Why does this occur? Well, the polymer, like the bentonite, is sensitive to the chemistry, but so is the polymer. These polymer hydrogels are sensitive to the liquid that's hydrating them. And so in a lower ionic strength solution, what we'll see is that polymer, particularly the linear polymers, you can imagine the polymer just kind of expanding out through the liquid, hydrating in the solution, forming this long web of gooey, viscous material to block the pore space. That's what I show here on the left with this, what was so-called extended polymer with lots and lots of water molecules around it. Very viscous, doesn't want to move in the pore space. On the other hand, if I have a solution that's of high ionic strength that alters the ability of that polymer to be extended, and in fact, I get a coiled type of behavior like I see here on the right, very few water molecules associated with it, and that system is much more mobile in the pore space. Now we're trying to come to grips with how to be able to separate out what type of polymers are affected by different types of solutions. It's an area of research right now, unlike conventional GCLs, where we pretty much know the geochemistry, the coupling of geochemistry and physical behavior in those materials. The Bentonite Polymer Composite materials are an area we're still learning a lot of things, but we do know, depending on the polymer we use, we will get different levels of gel formation with different ionic strength solutions. So making sure that the polymer we're using is consistent with the leachate that we need to retain is particularly important. And we're looking at some methods to be able to do that right now. Now, another fact that's important with bentonite polymer GCLs can be anions. For conventional GCLs, we talk all about cations. Calcium, sodium, magnesium, those are the key drivers. But with bentonite polymer composite GCLs, the anions can be important as well. The negatively charged anions. Are we dealing with chloride? Are we dealing with sulfate? Those are the two predominant anions in most leachates. Is it chloride rich or is it sulfate rich? And you can see that, for example, for this particular case, this particular bentonite polymer composite material, the hydraulic conductivity is very sensitive to the relative abundance of the chloride and the sulfate. If it's mainly sulfide rich or has a low anion ratio, it's very impermeable. If it's very chloride rich, that extended polymer conformation does not form, it coils and it flows out of the system, much more permeable. And we see that on the right here with another example. Again, more sulfate rich, more chloride rich, more permeable with the chloride rich. That's for this particular polymer. So it can be both the anions, the cations, and the ionic strength. It's a little more complicated. Just an example of why that occurs in that previous slide. Well, when it's a very chloride rich or high anion ratio solution, I don't get that elongated extended polymer structure. And in fact, I get a collapse of the polymer. And that's what I see here with the scanning of electron micrographs. Get what's a so-called pearl necklace type of structure where I have a strand with essentially clumps of polymer. The polymer itself is collapsed. There's very much less amount of water affiliated with those polymer surfaces. On the lower photograph is a in a sulfate-rich solution for this particular polymer. You can see it's very stringy, fine textured. That's the extended polymer structure. And when it's hydrated, that is full of water molecules. And those water molecules are immobile, right? And so that's in the lower photograph. You can imagine that just being this gooey, viscous gel that forms. And the shape and the behavior varies from completely different conditions depending on the anion. So matching the polymer to the condition is that we need to contain is important. One of the ways we're looking at that is a parameter called flow stress. Essentially, the flow stress is a property of a polymer for a particular hydrating liquid, beyond which, when we exceed the flow stress, the polymer ceases to behave like a solid and flows like a liquid. So you can imagine, if we're talking about polymer elution, we're interested in conditions that have high flow stress, which would mean that I have to get a lot of shear stress imposed in that polymer to get it to move out of the pore space. And so we've been studying flow stress, and that's going to be important, as we'll see here on the next slide. This is showing flow stress versus moisture content. And we can see at high flow stress, we'll tend to retain the polymer in the pore space, and it will have very low hydraulic conductivity. At low flow stress, we'll tend to have polymer eluting and much higher hydraulic conductivity. And we can see that down here in the photographs on the lower right. The lower photograph, a hydrated polymer with high flow stress, it looks, it's a gooey, viscous gel. On the right photograph, it's much more liquid-like. You can see it in this diagram right here. It's very dependent on the moisture within the GCL. As the GCL imbibes more and more moisture, the flow stress tends to diminish. So flow stress can be an important variable, and it turns out we'll use that as an index test in a bit. We measure that with a dynamic viscometer, as I showed in the previous slide. And we'll talk a little bit more about that in a minute. And so just an example here, these are some BPC-GCLs with 50 millimolar calcium chloride solution. And depending on the flow stress with the different BPC-GCL we're using, we have hydraulic conductivities ranging from around 10 to the minus 6 centimeters per second, very permeable, with a BPC-GCL that has low flow stress in the polymer. High flow stress are very resistant to movement or elution, very low hydraulic conductivity. So orders of magnitude variation depending on the relative mobility of that polymer and underneath the hydraulic gradient. Now you can imagine too that as the polymer ages, that flow stress might change as well. That's one of the things we've been working on, and I'm going to just show a quick video to illustrate this, and hopefully this comes through with the bandwidth. Just takes about 15 seconds. And then we're going to start wrapping up. But you can see here in this example, 3 different jars that we've aged at different temperatures, 20, 40, and 60 degrees C. Same original GCL polymer that we began with, just aged at different times. The jar on the left has a very viscous, almost like a jelly. That's a lower temperature, very short duration aging. On the right, longer, higher temperature, longer aging, changing essentially from a gel shown here on the left over to a liquid on the right. And you can imagine that gel is going to be very immobile, whereas that liquid polymer push right out of the pore space. So we've been studying the effects of aging on service life, and we see that that flow stress of the polymer does change. They're very accelerated experiments that we're going to be doing some time temperature modeling, a lot like we do for geomembranes, to look at the service life of these materials. All of our data indicate right now, though, that the products that are on the market right now have very long service lives when our testing indicates that the hydraulic conductivity is low. We'll talk more about it, and there'll be more information on that forthcoming. So let's finish up here in the last few minutes of the webinar. Let's talk a little bit about hydraulic conductivity testing. I showed this slide last time. It's a flexible wall permeameter. It's got a GCL inside, and we've got hoses going in and out, which are carrying the liquid in to the influent and the effluent out of the back end of the GCL. And we normally run hydraulic conductivity testing with GCLs using ASTM D6766 or an equivalent in international standard. It's a standard method. And key factors are prehydration condition, effective stress. We talked about these last time. But we also look at whether the test has reached hydraulic equilibrium and chemical equilibrium before we terminate it. Now, D6766 was developed for sodium bentonite GCLs, and the hydraulic and chemical equilibrium criteria are so-called termination criteria in those test methods were driven around the hydrologic and geochemical processes occurring in a sodium bentonite GCL and not necessarily a bentonite polymer GCL. So when we look at these termination criteria, one, we look for steady hydraulic conductivity, that it's not going up or down. That's pretty standard. We talked about that last time. We want to have some sufficient volume of flow, and that D6766 requires at least 2 pore volumes, unless the requester specifies something else. We look for steady flow, that we're getting flow in and out. And then the last one, and perhaps most important from a chemical point of view, is that the electrical conductivity, the effluent and the influent is the same. And for a conventional GCL, that means that the chemical reactions between the leachate that's being used for permeation and the bentonite have reached equilibrium, that the chemical reactions between those two are complete. When the solution that comes out of the GCL replicates what goes into the GCL, has similar electrical conductivity, that means that the chemical reactions are over. That's what we use for looking at termination criteria in a conventional sodium bentonite GCL. That may not be sufficient for bentonite polymer composite GCLs. We don't know, or let me phrase that a little differently. We're developing additional criteria specific to bentonite polymer composite GCLs. And just to illustrate why that's important, a couple of graphs, and we'll be finishing up here in just a couple of moments. Just a couple of data sets to illustrate some phenomena. What I show on the upper graph here is hydraulic conductivity versus pore volumes of flow. And we see this BPC-GCL is running along. It's very, very impermeable, 10 to the minus 9 centimeters per second. In fact, at these last data points here, the geochemical criteria in D6766 were satisfied. So we would look at that test. It looks like, except for not meeting 2 pore volumes of flow, it's in equilibrium. Well, we go a few more days, and all of a sudden it jumps up much more to a much more permeable state. We've flushed out some of the polymer it's eluted, and it became much more permeable. Why that is, or do we have a termination criteria, and do I identify that, is not something that we have fully identified and vetted yet. So that's forthcoming. A graph I show on the right is another example here for tests that run for more than a year, for a very, very long a period of time, with essentially this hydraulic conductivity, which is unchanged. I'm actually doing these at 2 different temperatures, looking at accelerated aging at 60 degrees C. And here we've got 6 to 10 pore volumes of flow at very, very low hydraulic conductivities. This test too had been in chemical equilibrium below 2 pore volumes of flow, at least defined based on ASTM D6766. What differentiates these two is the mobility of the polymer. In one case, the polymer was eluted, and the other case not. And we need to understand the difference. And we'll be putting forth some proposals to D6766 for new additional termination criteria going forward. Recognizing this, it's important that we run tests as long as practical. And I know academics think of things that are practical in a much different world than people have to make a living in industry, running tests and building projects. And so what we think of as a practical time, or a year or 2, is not practical in practice. But my recommendation is, at this time, run the test as long as practical until we develop additional termination criteria. Be prepared that in some cases, that test can take a very long time to come to equilibrium. We do have, in our laboratory, we'll see tests will take at least 2 months, but sometimes 6 or 8 months to reach even the termination criteria in D6766. So it can take a very long time before we have an answer. So are there some things that we can do ahead of time? Some things that will tell us, will this bentonite polymer composite work have a high chance of functioning with this leachate before I run 6 to 8 months of testing for very high cost? Is there some test I can do, like a swell index test for conventional bentonite, that will tell us whether it's likely to work? So things we might think about, well, for example, we talked about flow stress earlier. This is hydraulic conductivity versus flow stress. And flow stress on its own is helpful when you're looking at a single leachate and varying the ionic strength with a single polymer and a given bentonite. It works. You'll get a unique relationship between hydraulic conductivity and flow stress. But when we start looking at different liquids and different polymers, the uniqueness of that relationship fades away. And you see that here in this graph where we've got different GCL products, different permeate solutions. We just really don't have a relationship between hydraulic conductivity and flow stress. Same thing with swell index. We see that over here on the right, because again, it's the polymer flow stress that's eluting, but there's also a swelling phenomena of the bentonite as well, which we'll talk about again in a minute. Some have suggested let's look at swell index of the BPC. That in itself is not sufficient either. We see in some cases we'll get very little swell and have a very impermeable bentonite polymer composite, and on the other hand, a very permeable bentonite composite. So there's not a unique trend with BP swell index. Neither of those parameters on their own are indicative of whether the conductivity is going to be low. And the reason for that is that neither parameter on its own represents the key mechanisms. The mechanisms we talked about earlier is does the bentonite swell and does the polymer fill the voids between the bentonite granules? And we need something that actually captures both of those phenomena. And what we've been looking at is something we call flow swell index, which is a combination of the flow stress and the swell index of the bentonite component, not the bentonite polymer composite. So it's the product of those two, flow stress versus swell index. And we see with the so-called flow swell index, we could get a very nice distinction between high hydraulic conductivity GCLs and low hydraulic conductivity GCLs down here. There's an abrupt, almost a step function where it drops off going from high to low, and in that very narrow transition zone between the two. Now, we haven't fully vetted this phenomenon. We have a couple of papers coming out on it, but this does look to be like a very convenient test. It's not as simple as a swell index test, but it is a test that you can run in a matter of 2 or 3 days for modest cost and be able to get a sense for whether the bentonite is going to function adequately with that particular leachate before you run 6 to 8 months worth of testing. So let's just wrap up here. Some implications. BPC-GCLs are effective for many aggressive leachates. They work in applications where sodium bentonite is just too permeable. And they work by polymer gel clogging pores between the granules. And in some cases, even if the granules don't swell at all, right? And so the amount of swelling of the granule, you can imagine when there's more swelling of the granule, the polymer needs to do less work. There's less swelling of the granule, the polymer needs to do more work. Matching the polymer to the particular leachate that we've got is going to be important. The chemistry does affect both materials, the polymer and the bentonite. The variables that we looked at before, ionic strength, RMD, are both important. Add in a couple of mores. Anion ratio, the ratio of chloride to sulfate, and pH can be very important as well because they alter the polymer in addition to the ionic strength and the RMD altering both the polymer and the bentonite. So the chemistry is going to continue to be important, and matching the polymer with the chemistry is critical. These are pore clogging phenomena in bentonite polymer bentonite polymer composite GCLs. Swell index is not a good indicator. It doesn't work. All the data we have would suggest that it's not going to function properly or give us the right indication of low hydraulic conductivity. This flow swell index seems to be a useful indicator. We're developing that now. We've got some publications coming out, and it's something that we can measure in a couple of days. Some other implications, this termination criteria in D6766, we need to amend those for bentonite polymer composite GCLs. D6766 is not in its current form enough to validate whether we've got a true equilibrium condition. I don't have a great answer for that right now, except for run the tests as long as practical with our current standard methods. We have seen that if we get past 2 pore volumes or flow or so, then the GCL tends to remain steady, 2 or 3. But we've got to develop some other criteria looking at the chemistry of the effluent to be able to evaluate that. Finally, one of the topics that keeps coming up as I talk to people is how long are these polymers going to last? It's the same question we ask about geomembranes. They're going to last a very long period of time, like we see with geomembranes. But exactly how long, I can't tell you at this point. We're studying that right now, how aging the polymer affects its propensity for elution and the long-term hydraulic conductivity. So look for information on that that's coming forward, and look for more information on D6766. So I hope this was helpful. We have almost 100 people who've joined today, which is wonderful. We've got about 20 minutes left before we have to stop, where we can take questions. And anything that you've got to ask, I'm glad to answer. You can just put them in the question category, and I'll look them up. Oh, I already see some of them early on. Yeah, I see questions. Do the full screen, yeah. And the screen isn't working from Karen. Thank you. Early on, I catch that now. Full screen, I tried to do my best with the full screen. It just wouldn't work. When I did that for something with this webinar systems, just stopped functioning. We tried it earlier. I just don't know what happened. Okay. Is there an impact to internal or interface shear strength in relation to a sodium bentonite GCL? And this is from, I can't read the full name. For some reason, I can't seem to pull this out, the full comment out, but from Ramachandran, is there an impact on internal interface shear strength? This is a fantastic question, something I didn't put in here, but is important. In fact, we've shared a little bit of this. The polymer is a very viscous but liquid-like material. And you can imagine that it has lower shear strength than the bentonite or the geotextiles. And if we have polymer elute in the interface, that will create a thinner, weaker zone. And so when we do interface shear testing, we want to conduct it with as a realistic condition as we can with the leachate of interest, because if we get polymer elution in that interface, it may alter the interface strength. There are also GCLs that are available that either use a slip film or a scrim reinforced geotextile that will tend to minimize elution or prevent elution, both out of the GCL and into the interface. But this can be very important. I'm glad, Ramachandran, that you brought that up. Next question. Are there differences between the granular types of bentonite polymer composites over a bentonite type of bentonite polymer composite? Excuse me, a powdered. So essentially, is there a difference between a bentonite polymer composite that's manufactured granular bentonite versus powdered bentonite? Don't have definitive data on that yet. This is a topic that we're very interested in looking at, something we're exploring right now. But you can imagine that as the bentonite granule size diminishes, the pores between those granules will be smaller, and it will be more difficult to fill those pores. So yes, we can imagine that there would be a difference, but I don't know specifically what it will be at this point. And I'm going to see, let's go to the next one. In light of lack of publications on service life, what is your view on testing the GCL without polymer for hydraulic conductivity tests? Well, so the question is really, given that we don't know the service life right now, you know, can we be confident in the products that we're using? I have complete confidence in what we're using. I don't think doing a test on bentonite, a conventional bentonite alone, is going to be relevant, because that's the condition that would correspond to all the polymer being released, which might occur sometime, might occur very far into the future, and might not occur at all. So we may have conditions where we get essentially zero polymer elution. but I have to be candid with you. I don't have a great answer for that at this time. Here's another one. What causes a different behavior among the phase-separated, intercalated, and exfoliated bentonite or polymer type? So is it the bentonite or the polymer or the processing, you might say as well, that creates different types of behavior? They're all really different. My discussion was largely about the phase-separated bentonite polymer composite materials. They function based on the two different components, the bentonite component and the polymer component, filling the pore space, and largely that polymer filling between the pores that the bentonite can't swell into. That's very fundamentally different from the polymer modified bentonites, the exfoliated products or intercalated products, where we've actually modified the surface of the montmorillonite with the polymer, which alters its interactions with water. And so the mechanisms are completely different. I can't tell you fundamentally how they would behave in a very systematic way for different types of liquids. For example, a polymer modified versus a bentonite polymer composite, because we just haven't studied that yet. That's an area of work coming forward. We found that the bentonite polymer composites work over this really broad range, provided that we get the right polymer for the liquid that we've got to retain. Something that will create a very viscous, sturdy gel in the liquid that we're trying to contain that doesn't elute. Next question from Calvert Barclay. Linear polymers interact with bentonite at the microscale. Is the same for cross-linked polymers, or is it purely mechanical in this case? Actually, I would argue that in the bentonite polymer composites, both the linear and the linear polymers and the cross-linked polymers are doing something very similar. They are filling the voids between the bentonite granules. So we saw that in the SEM, where we had a very small bentonite particle with a void between it, and then that void being filled with polymer. That was, in that particular case, a linear polymer gel. But the same thing can occur with the cross-linked polymers. They form somewhat of a different gel. It's less viscous, less fluid-like, but just as effective in filling the void space, and in fact can be more resilient to elution and chemical change. So it really depends on the particular leachate that we've got to manage, and the matching that polymer with the leachate so that the bentonite polymer composite will stay in, the polymer will stay in the pore space of the bentonite polymer composite. Here's a good question. What is your definition of granular versus powder? This is actually something I don't think we've settled in the industry. Granular bentonites tend to have average granule size between 1 millimeter and 0.01 millimeters. So in that range, and let's say between about 0.01 to 1, and maybe an average of about 0.1 millimeter would be typical from a lot of my experience. The powders tend to be about a factor of 10 lower than that, but we need to develop a better definition of polymer, of granular versus powdered. And we really need to study whether, how the different granule size distributions or particulate size distributions alter the hydraulic behavior. Another question is from Jimmy Youngblood of Solmax. Will you still need polymer after reaching high stresses at the end of a life of a landfill? Well, that depends. If we have it deep enough and the leachate is not too aggressive, even if we lost all the polymer, it still might have very low hydraulic conductivity. But we also know, for example, a sodium bentonite alone, if it interacts with a very aggressive leachate and doesn't swell sufficiently, even under high stress, it will retain very a hydraulic conductivity that in many cases will be too high. So it really depends on the particular leachate that you're managing and the stress condition. And we have good literature on good data on the effect of the influence of overburden pressure on conventional GCLs that are both those that have been altered by the geochemical interactions that have become more permeable and those that have not. And I'll be glad to share that if anybody's interested. Here's a good question. Is there any polymer treated calcium bentonite? Calcium bentonites may be more useful than sodium bentonites in terms of cation exchange. This is from Yasin Karakas. Yasin, I don't know the answer to that. I haven't seen a polymer, let's say a bentonite polymer composite with a calcium bentonite. Good question. I don't know. That's a good question. I haven't seen that yet. That's something that we ought to look at. And then finally, I've got one. Hossein, do BPC-GCLs have the same advantages on vertical surfaces? Is the real application of conventional GCLs due to installation faults? We saw more hydraulic conductivity of vertical surfaces than horizontal surfaces. I don't know the answer to that question specifically, vertical versus horizontal, but from a material property point of view, they should be independent. Horizontal, vertical, it's really not the orientation in which we place the GCL, but whether the material that's contained within the geotextiles has a pore space that yields very low hydraulic conductivity. Now, we can imagine that installing something on a vertical, for example, on a cutoff wall, it's going to be much more difficult than on a horizontal, like on a floor of a landfill. And so I could see where you might have more installation defects, particularly at an overlap from a vertical installation. Now, if we were looking at a vertical installation up against a wall, that might be something very different. And I don't know the answer to that up against a wall. Trevor Walker. Hi, Trevor. Good to have you with us. Trevor is with Husker. Why is there such a difference in hydraulic conductivities for BPCs permeated with ionic strength of about 0.6 molar? Or 600 millimolar. The BPCs loaded with 6.5 and 6.4% of polymer compose the upper and lower bounds of hydraulic conductivities in this portion of the graph. It seems that like there are almost 4 orders of magnitude difference between BPC-GCLs with about the same polymer loading. Really great question. We can have the same polymer loading in a GCL, but a different polymer, and it will behave differently with a given solution. So we may be able to have one polymer which retains its very viscous, durable structure in the liquid that we're trying to contain and is very difficult to elute out of the pore space. Whereas we might have another polymer, same exact polymer loading, but it tends to be less viscous and more fluid and is more readily eluted. And so you can get the same polymer loading, but different, essentially, polymer properties which affect its ability to be retained in the pore space. And that's why we're developing these tests that allow us to look at the product and say, can I run an index test within a few days with, for example, as I showed here, this flow swell index, where I can look at different products that may have similar polymer loading, but different polymers, and give us very different outcomes. We need some type of screening test that will allow us to answer these type of questions straight away early on before we spend a lot of time, months of testing. Good question, Trevor. You can see that in some of my answers too, I'm hedging some, in part because this is a developing field. You know, I've been working on GCL materials and interaction of bentonite and solutions and the geochemistry of those interactions for 30 years. And conventional bentonites, that's a pretty well understood phenomenon. And this is a newer area where we're learning new things. Tarek, good to have you on as well. Tarek gave a really good webinar a couple of weeks ago on Bentonite Polymer Composite GCLs as well. Tarek and I go a long way back. Tarek was a PhD student of mine back in the 1990s, which seems like the dark ages, last century, and as a professor at Florida State University. Thanks for joining, Tarek. Is prehydration as important to BPC-GCLs as conventional GCLs? There's a lot of discussion and debate about this right now. We've studied prehydration in the context of subgrade prehydration and don't find that we get a significant amount of benefit from subgrade prehydration. The whole prehydration phenomena and how that influences the hydraulic conductivity of bentonite is a very difficult and complicated area of study, but we can understand those processes. What we do know what happens when we prehydrate a bentonite. Essentially what we do is get it in an osmotically swollen state with a very dilute solution. And in some cases that can create a bentonite that's more resilient. And so, but we haven't studied that broader context of full prehydration prior to permeation with liquids of interest, largely because in most applications in the field, we don't have that opportunity to essentially prehydrate the GCL a priori. We put a GCL down dry, we cover it up with a gym membrane, and it hydrates from below from moisture moving up from the subgrade. That's what we call so-called subgrade prehydration. And that subgrade prehydration does not provide enough moisture to create a permanent osmotically swollen bentonite like we might see in a laboratory prehydration experiment. So a long answer to a question about prehydration. And that's the last question. A lot of good ones here today, and we're just about out of time. This is great. Really appreciate it. And I apologize that we had some difficulties with the PowerPoint. I don't know what happened. We had it all running beautifully right before the webinar this morning, and as soon as we press start, things changed. But I believe you're able to see the slides. I will post these on a file share for you to be able to download, along with the CEU certificates, and I'll put all the publications I've cited in here on the website as well, so that you can download those too. Any other questions before we wrap up? Okay, well, I think that's it. I want to thank everybody for coming today, spending an hour and a half with me, learning about Bentonite Polymer Composite GCLs. These are fascinating materials that really provide us with opportunities to create barriers and systems in which other materials just won't work. And we have a lot of those conditions in industry that we got to deal with, and these are great products for those applications. So, and please look for more research products and continuing information coming out on these as we go forward. There's a lot of active study in this area. We're doing some of that work. Others are as well, both in industry and academia. So please be on the lookout for more information as you go forward. Thanks a lot.